Hello, in this video I'm going to solve the problems in quiz number 1. The first question, how many prime factors does 42 have? You need to choose one of these options. It's an extremely simple question. What you need to do is to factorize 42 and write it as a product of prime numbers. You already know how to do that. So for example, the way that I do it, I put 42 here and I draw a vertical line and I put prime numbers here on the right hand side in a way that 42 is divisible by those numbers, and I do this process, and this process will always end when you reach 1 here. Okay, for example, I would ask myself, what is a prime number for which 42 is divisible by? So example, one of those is 2. So I put 2 here, and then I divide 42 by 2, it becomes 21. Then I ask the same question again. What is a prime number so that 21 is divisible by that prime number? The answer is 3. So then it becomes 7. And I ask the same question, what is a prime number so that 7 is divisible by? The answer is 7 itself. And then when I do division, I actually see that the remainder is yeah. So I reached to this point that I wanted to reach. Okay, so I stop here, and then 42 is the product of these prime numbers. So one of them is 2 multiplied by 3 multiplied by 7. So the option that you have to choose is that there are 3 prime factors for 42. Okay, question 2 now. Consider the following congruency relation. If r is an integer such that r is greater than or equal to 0 and is strictly less than 13, then what r is? Okay, so it's a congruency relation. The module that I'm working in is 13, and you see that I have a lot of numbers that are appearing in the base and are greater than 13. If you remember what I said when I was teaching you this topic, I told you that whenever you have a congruency relation, every base which is above the module can be replaced by a smaller number. Okay, so you can choose different names for the numbers that appear in the base. So for example, 40, when it comes to module 13, can be written as 1. Why is that? If you want to see this, the reason is that the left hand side 40 minus the right hand side 1 becomes 39, and 39 is divisible by 13. So this means that when I decide to work in this module 13, a good name for 40 is just simply 1. What is a good name for 64 in this module? So 64 is congruent to minus 1 module 13. Why is that? Because the left hand side 64 minus the right hand side, which is minus 1, becomes 65, and 65 is divisible by 13. So this means that 64 is congruent to minus 1. Okay, for this one I can also find another name, but instead of doing that, I see that this is congruent to 0 module 13. Why is that? Because 26 minus, so let me write the congruency relation first. So this becomes this. This is a true congruency relation, because the left hand side 26 minus the right hand side 0, it becomes 26, and 26 is divisible by 13. So I don't care what this is, because whatever this is, this will be multiplied by 0, so I don't need to be worried about spending time to understand what 75 is. What about 15? 15 can also be written as 2 module 13, for the same reason. 15 minus 2 is 13, and 13 is divisible by 13. So finally, what I can write 40. I just copy and paste the left hand side. Yes, and then I start replacing what I found here. So instead of 40, I put 1. Instead of 64, I put minus 1. Instead of 26, I put 0. Instead of 15, I put 2. Yes. And then of course I can simplify this one more step. So -1 to this power is just -1 because this is an odd number. So if I multiply -1 by itself odd number of times, it becomes -1. -1 multiplied by 1 is just simply -1. Yes. The next one, this number is of course 0. 0 to any power is 0. So when I multiply it by 75, it remains 0. And then instead of 2, I just simply write 2 itself. And then if I do this very simple calculation, -1 plus 0 plus 2 is just simply 1. And that is the answer that you have to write here. So the solution is r equals to 1. Okay, question number 3. Here we are supposed to find GCD of these two numbers. We also need to find the LCM of the same pair of numbers and then add them up and write the answer here. Okay, so you have to show your calculations. So in order to find GCD and LCM of a pair of numbers, we factorize them into a product of prime factors. So I will do the same thing as I did in problem 1 for 36. So I divided by prime number 2. The quotient is 18. I divide it again by 2. It becomes 9. I divide this time by 3. It becomes 3. I divide another time by 3. It becomes 1. So this means that 36 can be written as the product of 2 times 2 times 3 times 3, which I can write it as 2 to the power of 2 multiplied by 3 to the power of 2. And I will do the same thing for 54. Okay, so 54 is also divisible by prime number 2. It becomes 27. Then it is divisible by the prime number 3. It becomes 9. Divided by 3 once more, it becomes 3. Divided by 3 once more, it becomes 1. So this will give me that 54 is equal to 2 times 3 to the power of 3. Okay, but in order to find GCD, I need to find the common prime factors. So here the prime factors involved are 2 and 3. Here the prime factors involved are again 2 and 3. So the common factors are 2 and 3. Okay, so what we do, we write GCD of 36 and 54 is equal to, the common factors are 2 and 3. For LCM, I not only need the common factors, but if there is any factor, I have to bring it in. But of course, in this case, we have only prime factors 2 and 3 involved. So then again, I have to write 2 and 3. For GCD, you need to choose the lowest power that appears in these two numbers. For example, here, if I ask you what is the exponent of 2 in number 36, the exponent is 2, and here the exponent is 1. You choose the lowest one, which is 1. And again, between these two, here the exponent is 2, the exponent is 3, you choose the lowest one, which is 2. And then you calculate that. So it becomes 2 times 9, which is 18. So the GCD of these two numbers, the greatest common divisor, is 18. And now here, for LCM, you choose the highest power, highest exponent. So here, 2 to the power of 2 to the power of 1, I choose 2 to the power of 2. And here, I have 3 to power 2 and 3 to power 3, I choose power 3. And then 2 to the power of 2 is 4, 3 to the power of 3 is 27, and if you multiply them, it becomes 108. So this means that if I add these two numbers, GCD of 36 and 54, plus LCM of 36 and 54, it becomes equal to 18 plus 108. So the answer becomes 126, and 126 is the number that you have to type in this to get the points. Okay, now the next question. Let a be an arbitrary integer. So arbitrary means we don't fix a. A could be any integer, and we want to see that independent of the value that we choose for a, what the value of r is. So if 3a plus 2 squared plus 33a is congruent to r modulo 9, and where r is a non-negative integer less than 9, then what r is? Okay, that's also a very simple question. So what you do, you know that, for example, here I have number 3 and number 2 and number 33, all of them are appearing in the base as a base, and then one of them is only above 9, 33, so I can reduce 33 to a smaller number when I'm working in module 9. But if you don't mind, before doing that, let me also open this up to see if we have more numbers that I can simplify. Okay, so what I do, I start from 3a plus 2 squared plus 33a. I expand the left hand side, so you see that I have put equality sign for the time being, so this becomes the first one squared 2 times the first one times the second one, and finally the second one squared. So the first one squared is 9a squared, 2 times the first one times the second one is just 12a, and then I have the second one to power 2 is 4, and then I have a 33a at the end. And I know that I can simplify these two. For example, I take 33a and 12a together, so it becomes 9a squared plus 45a and then plus 4. Now I start simplifying things modulo 9. Yes? Okay, so if I ask you what is 9 in its own module, 9 is 0. So 9 is congruent to 0 modulo 9. Why? Because 9 is divisible by 9. In other words, 9 minus 0, which is 9, is divisible by 9. So a good name for 9 is 0. So instead of 9, I put 0. So it becomes 0a squared plus. What about 45? 45 also is 0 modulo 9. Why? Because 45 minus 0 is divisible by 5, is divisible by 9. So 45 minus 0 is 45. 45 is divisible by 9. So this is also 0. And then 4 is just simply 4. Okay? And then of course 0 times a squared is 0. This is also 0, so 4 is left. And then I get 4 modulo 9. And 4 is acceptable because if you see, they have asked you find r so that r is non-negative and less than 9. So this is non-negative and less than 9. So simply you type 4 in this box. Okay, let us solve the next question now. Let a and b be natural numbers such that their remainders when divided by 7 are 2 and 4 respectively. The remainder of 2a minus 5b by 7 is equal to, so we need to find the remainder of 2a minus 5b by 7. Okay, so let us use congruency to solve this problem. Of course, you can use division algorithm as well, but let us just do this congruency method first. So we see that if I divide a by 7, the remainder is 2. What does it mean? It means that a is congruent to 2 module 7. Yes. And then when I divide b by 7, the remainder is 4. So what does it mean? It means b is congruent by 4 module 7. But now I want to know if I divide this number by 7, what will be the remainder? So this means that I need to ask this question from myself, that if I simplify this module 7, what will be this number? But I have to give this number in a way that it is non-negative and less than 7. Extremely simple. So this I will immediately construct this combination using what I have. For example, I multiply the first one by 2, so it becomes 2a is congruent to 4 module 7. I multiply the one below by minus 5, so it becomes minus 5b is congruent to minus 20 module 7. And then I add these two congruency relations side by side, so it becomes 2a minus 5b. On the right hand side, 4 minus 20 becomes minus 16 module 7. So in principle I am done, but you know that this number is not acceptable as the remainder. I have to write a number which is another name for minus 16, and respecting this fact that this number should be non-negative and less than 7. And there is only one number with that property, and that is 5 module 7. Why this is correct? Why minus 16 is congruent to 5 module 7? Because the left hand number, minus 16, minus the right number, which is minus 5, becomes minus 21. And minus 21 is divisible by 7. So yes, this is acceptable. Is this acceptable as the remainder? The answer is yes, because this is non-negative and it's smaller than 7. So the problem is solved, and the remainder is simply 5. Of course, you can also do it using division algorithm, because when you say that the remainder of a by 7 is 2, using division algorithm, it means there exists an integer q such that a is 7q plus 2. Okay, and then when you see that the remainder of b by 7 is 4, it means that there exists probably a q prime in z such that b is equal to 7q prime plus 4. And then I multiply both sides of the first one by 2, so it becomes 2a is equal to 14q plus 4. And I multiply this by minus 5, so it becomes minus 5b is equal to minus 35q prime minus 20. And then I add these two side by side, so it becomes 2a minus 5b is equal to 14q plus 4 minus 35q prime minus 20. So if I simplify this a little bit, so 2a minus 5b, it comes equal to, so this number and that number is minus 16, but instead of minus 16 I write minus 21 plus 5. So then it becomes 14q minus 35q prime, and then minus 21 plus 5. The reason I did this, because I want to be able to factor a 7 out. So if I factor a 7 out, it becomes 2q minus 5q prime minus 3, and then plus 5. And of course this number, whatever it is an integer, so I can call it capital Q. So this means that this becomes 7q times 5 plus 5. And now look, this number is a multiple of 7 plus 5, and 5 is non-negative and less than 7, so this is the remainder. But my goal was to be able to solve this problem using this very simple method. Okay, so now let us go to the next question. Okay, here x is given to us. We are supposed to find its remainder by 8. So in principle we need to ask ourselves, if I simplify x modulo 8, what will be this number? And I have to express this number in a way which is non-negative and less than 8. But of course in this exam the calculator is not allowed, so you need to find a way to get rid of these very big bases. Okay, so what we do, we actually write 3 to the power of 40. So let me 44 plus 4 to the power of 33. My goal is to simplify this module 8. But I told you before that if you have a number in the base which is higher than the module, you can always simplify those numbers. Okay, but how can I do that? It's not that hard, because hopefully you immediately realize 3443. I want to see how many multiples of 8 I can pull out. So I don't think it should be hard to realize, even without calculator, that this number is 3200 plus 240 plus 3. Why I did that? Because I want to extract multiples of 8 out. And then if I ask you what is this number in module 8, I would say that this part becomes 0 because 3200 is divisible by 8, so it is congruent to 0 when you work in module 8. The same story is true for 240 because that's also divisible by 8. So this number is just simply 3. So as far as module 8 is concerned, a good name for this is just simply 3. And I can do the same thing for the next number, 4334. I can write it as 4000. My goal is to extract multiples of 8 out as much as I can, plus 320. So far 4320, and then I have 14 left. So 14, instead of 14, I can also write 8 plus 6. Yes. Okay, so now if I want to simplify module 8, then what happens? This is again 0 because it's divisible by 8. This is also 0 divisible by 8. This is also divisible by 8. So the answer is simply 6. Okay, now I would, instead of considering this, I throw this out and put 3 instead, and I throw this out and I put 6 instead. Yes, of course, if you want to, you can work with we can work with -2 as well. Yes, it might be -2 is better in this case, by the way. So let me continue and write this -2, because from magnitude point of view, working with -2 is easier than working with 6. Yes. Why is this correct? Because the left hand side minus the right hand side becomes 8, and 8 is divisible by 8. So now my question mark that I was looking for, so I would say the left hand side becomes congruent to module 8. Instead of this I put 3, and instead of this I put -2. And because this power is odd, so -2 to the power of 33 is the same as -2 to the power of 33. Okay, so what I do, I would write 3 to the power of 44 and then -2 to the power of 33. But then extremely simple. Why? Because instead of 3 to the power of 44, I write 3 to the power of 2 to the power of 22. And instead of -2 to the power of 33, I write 2 to the power of 3 to the power of 11. Yes? Why is that useful? Because 3 to the power of 2 is just nothing except 9. 9 to the power of 22 minus 2 to the power of 3 is just simply 8 to the power of 11. And now if I want to simplify this modulo 8, again, 9 can be written as 1. 8 can be written as 0, so this becomes 1, and 1 is acceptable answer for me, so I need to put 1 here. Okay, good. Okay, now let us solve the last question. The units digit of this number is equal to, this is the goal of this question, we have to find the units digit of this number. So what do I mean by units digit? For example, if I have a 3-digit number, say 123, the rightmost digit of any natural number is called the units digit of that number. And if you remember, during the lesson we had this remark that the units digit of a natural number is equal to the remainder of that number by 10. So what does it mean? It means that if I want to find the units digit of this number, I have to simplify it in module 10. Okay, so this is the question that we need to ask. 1 to the power of 101 plus 2 to the power of 202 plus 3 to the power of 303 plus 4 to the power of 404 is congruent to which number in module 10? But of course I want to have this number non-negative, and I want to have it smaller than 10, otherwise it cannot be a digit. Okay, so I want to solve these individually. I want to take care of each one of them individually. The first one is actually extremely simple. So 1 to the power of 101 is just simply 1. And of course, every number is congruent to itself in any module. So what I can write is that 1 to the power of 101 is congruent to 1 itself. Actually, it is equal to 1 module 10. So that is very, very simple. The next simple thing is 3 to the power of 303, because I have the ideal scenario, yes? I know that 3 to the power of 2 is congruent to -1 module 10, and you know that during the lesson I told you that whenever you have -1 or 1, you have the ideal situation, because raising it to high powers in a fast way is easy. So here my goal is to have this exponent, but I have 2, so I raise both sides to power 151. Okay, so I have to get close as possible to 303, but I'm not allowed to go beyond 303. Yes, so I raise it to power 151, the left hand side, and of course the right hand side simultaneously. Yes, so the left side becomes 3 to the power of 302, but the right hand side, because 151 is an odd number, remains -1. Okay, and then I need 303. I have 302 so far, so motivates me to multiply both sides by 3. So this becomes 3 to the power of 303 is congruent to -3 module 10. So let us keep it for the time being here. Okay, but about 4 to the power of 404 and 2 to the power of 202, the problem is a little bit more complicated. So what I want to motivate you first is that if I have two natural numbers a and b, whose rightmost digit or the units digit of both of them is 6, if I multiply them, the units digit of the product is still 6. So what I'm saying, actually, let me change my color. So I'm saying that if a is a natural number whose units digit is 6, meaning that it is congruent to 6 module 10, and if I have another natural number with the same property that its units digit is 6 again, meaning this, what I am claiming that this is the case that AB is congruent to 6 again, module 10. Yes? Why is that? Extremely simple. Why? Because I multiply these two side by side, so the left hand side becomes AB, the right hand side becomes 36 module 10. But 36 itself is congruent to 6 module 10. So that's it. So I was able to prove my claim. So why this is useful? Because I can use the same method. Instead of choosing two different numbers, I can choose b and a to be equal. If a and b are equal, so then this can be written as a squared is congruent to 6 module 10. Okay, now I take this one with the first one and multiply them side by side again. So what I get a to the power of 3 is again 6. Yes, because when I multiply them, this becomes 36 when I multiply them, but 36 is again 6. So a to the power of 3 is also congruent to 6 module 10. And then the same analogy you can continue and finally say that if a is congruent to 6 module 10, then for any natural number n, a to power n is also congruent to 6 to power 10 in module 10. So that was what I want to use here. So why this is useful? Because for 4 to the power of 404, I can start with this. So 4 to the power of 2 is 16, and 16 is congruent to 6 module 10. Yes? Now, what I do, I realize that if a is congruent to 6 module 10, a to any power remains 6 if I work with module 10. So what I do, I would say that 4 to the power of 2 to the power of 202 is still 6 module 10. Yes, so let me repeat. Here I was hoping that I was able to convince you that if a is congruent to 6, a to any power remains congruent to 6, of course, if I am working in module 10. This is something simple because 4 to power 2 is 16, minus 6 is 10, and 10 is divisible by 10. So this is a true statement. Now, because this module is 10 and the right hand side is 6, I give the role of a to 4 to power 2. And then I use this and I give the role of n to 202. So I will have that one. So this means immediately that 4 to the power of 404 is congruent to 6 module 10. That's it. Okay? But now, for this one, that is also simple because 2 to the power of 202 can also be written as 4 to power 101 and do the same strategy as I did here. So for example, 2 to the power of 202 can be written as 4 to the power of 101. But 4 to the power of 101 can be written as 4 to the power of 2 to the power of 50 multiplied by 4. But now if I want to write it in congruency 10, yes, so what happens? 4 to power 2 is congruent to 6. So 4 to power 2 to any other power, if I am working in module 10, remains 6. So this becomes 6 times 4, which is 24, yes? But 24 itself is congruent to 4 when I am working module 10. So finally, I realized that 2 to the power of 202 is congruent to 4 module 10. Okay? Now, if I start adding this to this, to this, and to this, I am done. So what happens? The left-hand side becomes 1 to the power of 101, 2 to the power of 202, 3 to the power of 303, plus 4 to the power of 404 is congruent. The first one is 1, the second one is 4, the third one is minus 3, and finally the last one is 6. So, and if you simplify this, so this becomes 8 module 10, and 8 itself is acceptable because it is non-negative and it is smaller than 10. So you have to put 8 here. Okay, until the next video, be safe and goodbye. Thank you.